Hello again and welcome. So on my right I have the Fluke 189 that I just transient tested. Again, I bought this meter just for the purpose of running that test. And the only thing that's really wrong with this meter, at least electrically, is that it has a missing spring contact in the switch. So one of the things I had mentioned is that I'd replaced the Supercap on my Fluke 189. And this is the part. I'm not sure how well this will show up on the camera. This part is made by Panasonic. It's a part number EEC S0HD104H. The diameter of this part is 0.413 inches. It's 100 millifarads and it's a 5.5 volt part. Now this is a through-hole device, and what I've done is, you can see I've kind of bent the leads up and it just fits in there very nicely. I went to look on DigiKey and they now show this part is no longer available, but one of the viewers looked this up in a distributor in their area and they found somebody that had it in stock. Let me just turn on our old meter and let's look at the voltage across this Supercap. So again, there's nothing in here, it's just an open circuit, and you can see it reads 3.212. Somebody had mentioned about putting a 3.3 volt part in there. If you look at the equations that some of the manufacturers supply that show how to calculate the life of a Supercap, there's basically two things that feed into that. One of them is operating temperature, the other is the operating voltage. It's pretty common that I'll derate parts like that in designs anyway, so that's how I ended up with this 5.5 volt part. A lot of people had written and just said that they leave them out, so that's certainly an option if that's what you're after. So because this meter did so well in my testing and it's in such good condition, except for that switch contact, I thought I'd go ahead and put a new Supercap into this board. So I've got one here. This again is one of the Panasonic parts. It's the same part that I had in this meter. So let's just go ahead and install that. Alright, all I'm going to do is remove the flex cable along with the backlight. Just kind of get it out of the way. And we'll just tack this thing down real quick. Make sure we get it in the right direction. And again, you can see the part just lays right in there. One of the tests that I didn't perform was where I removed the two fuses and then I applied the 2000 volts. And I had mentioned that the reason I didn't perform that test is because the wattage rating of these two resistors, I'm afraid, is just too low, and I would probably just damage these two resistors. If you look at that video where I purchased that brand new Fluke 87V, again, they changed out the size of the resistor in that meter, so the lead spacing is quite a bit wider to accommodate that larger part. Now, we don't have that option with this particular meter, so I was looking for a smaller body like this that may be able to work. So again, if you're curious where I'm getting this from, this is out of 61010-2-033, and this is section 101.3.2. And again, here we can see if the protection device is a fuse, it's replaced with an open circuited fuse. The voltage of 2 times the highest rated voltage for any terminal is applied to the terminals of the overcurrent protected measuring circuit for 1 minute. The source of the test voltage shall be capable of delivering 500 VA. During and after the test, no damage to the equipment shall occur. Behind the clock, you can see I have my attenuator out. This is hooked up to one of our high voltage power supplies. So again, the last time I ran a test like this, I used this resistor right here, and you can see physically the part is the same package, it's the same value, different tolerance, and this resistor was damaged. So these are made by TE. These are an ROX series. You can see it's basically a mega ohm. We're going to start with this resistor here. Nice thing about this would almost drop right in. So let me just go ahead and we'll turn up our power supply. Again, this is a divide by 10 attenuator. So 200 volts on this meter is 2000 volts across our resistor. So about 2020 volts. And we'll just let this set for a minute. So again, 2000 volts across a 1 mega ohm resistor, it's going to dissipate 4 watts. This particular part is a 2 watt device, but because it's only got to hold this for 1 minute, we may be okay with it. I'd be a little concerned about the voltage breakdown. I can smell it right now. It's definitely starting to heat up. You can see next to the virgin parts, it didn't really discolor at all. Let's just check the value. Boy, pretty close. Now these are a part by Ohmite. This is a Mach 500 series device. A little more expensive, but these are rated for the voltage that we want to put across it. And you can see again, it reads 1 mega ohm. Let's just give this one a try. Get about 2020 volts. Again, I'm not smelling anything burn. Okay. Again, I'm not smelling anything. It's definitely hot. Let's go ahead and check our resistance again. You can see it's hardly changed, and again, no discoloration. Now this part is made by SMV. This is a 3 watt device. You can see it's surface mounted. Breakdown voltage of this part is pretty good. You can see 1 meg. Let's go ahead and hook him up. I want to make sure I've got it right in the jaws. Here we go. Now the nice thing about these parts, this part would solder right across where the pads are for the original resistor. I still think that we'd be better off with these, just from a mechanical standpoint. Alright, so the resistance looks pretty good, 987K. Again, there's no discoloration on the package. So what I'm thinking to do is just rerun this same resistor at a higher voltage and maybe run it for a little longer. So again, that's 2,500 volts, and let's just let it cook for 2 minutes. Oh, it's starting to discolor. It's pretty impressive. You can see we've definitely discolored it. Let's go ahead and check the resistance. It still looks real good. That's one tough resistor. So again, this part is made by TE, and it's a part number ROX2SJ1M0. The problem that I see with using this is this part's rated for 350 volts. That's the working voltage. They give a max surge voltage of 750 volts with this. That's it. So again, we're applying 2,500 volts at this point. It's doing quite well, but we've definitely far exceeded what this part is rated for. You can see I've gone ahead and removed our 2 resistors. Again, that's here, and these 2 pads here. You can see I trimmed this resistor's leads. Again, this is the surface mount part. So I just bent the 2 leads out, and then I took a set of dikes and I cut this lead in half. And you can see this can now fit right in the board like so. But you see there's a little bit of overlap. Now, if I flip this around, it brings it in a bit. It's almost flush with the board. So that's not a bad fit, but what I don't like about this is once this is installed into the case, the side of this resistor is actually touching the plastic case. The other thing I don't like about this, you can see if I insert this into the other set of holes, get some light in here, there we go. You can see there's an interference problem, so this will not lay flat. There's a capacitor right here that sits right underneath this part. So of course with the axial leaded devices, that's not an issue. Alright, so this is our Ohmite Mach 500. And you can see it'll fit flush with the board, but you really have to bend the leads on a pretty tight radius. And again, you could probably bend this thing inwards enough to keep it away from the plastic case. If we look at the other placement again, there's no clearance issues here. The other option would be to use this device here. Again, it's a 2-watt device and it's only rated for 350 volts. Now, of course, this device is going to fit without any problems at all. From a fit standpoint, this is definitely our best choice. I'm not sure what the voltage rating is for these old parts. I suspect it's probably on par with what we have here. Of course, this resistor is flame proof and it's also surge rated, so there's probably some advantages to going to this part over what the meter had originally anyway. Really what I'd like is for the lead spacing on the pads here to be a little bit wider and have this part away from the edge of the board a little bit farther, and then I could go ahead and use a larger part. So I'm leaning towards this resistor here. This is the resistor that I've been stress testing. Again, it's hooked up to our high voltage power supply. The Bryman on the right now is in series with the resistor, so this will be measuring the current in microamps that's going through our resistor. And again, the Bryman on the left is looking at the voltage across it using our 10x attenuator, again behind the clock. So again, 250 volts on this meter equates to 2,500 volts across our resistor. So what I'm going to do is just go ahead and turn up the voltage, and I'm just going to let this thing set until it fails. You can see it's roughly 2.7 milliamps. I don't know if you can see the smoke coming off of the device. This is 2,517 volts across it right now. Again, the part is only rated for 350 volts. That's the working voltage. You can see the current's going up a little bit. You know, I didn't clean that part, but it's possible some of that smoke is just the oils off of my fingers. Looks like the camera shut off, but you can see it's been running for about 15 minutes. I'm just going to let it continue to sit. It only has to run at 2,000 volts. So we're higher up on voltage, and has to run for a minute. And of course, we far exceeded that as well. You can see I have my calibrated dead fuse, and I've gone ahead and I've replaced the 2 resistors. Again, we'll just start with the milliamp side, and we'll apply 2,000 volts for our 1 minute, and let's just see what happens. There we have it. It's 2,000 volts. It's drawing about 2 milliamps, 2.2. Let's repeat our test with the amp side. Again, that's this resistor here. So it's drawing roughly the same amount of current. There you go, it looks fine. I'll switch it to amps. And let's install one of the leads. There you go. Let's try it in the microamp. And there you go. Let's try plugging them both in at the same time. You can see we get the lead error on both. Let's try amps DC. Same thing. There's our error. And let's go ahead and insert our lead. And let's try the microamps DC. Alright, so it looks like the meter survives that test just fine. It may actually survive with just the regular resistors. I don't know, I didn't try it. But but I would say that that's probably the weak point of the circuit is the resistors. But it looks like the rest of the sensing circuitry doesn't have any problems with the 2 kV. The same thing with any of our clearances. I didn't see anything break down, so that all appears to be fine as well. So again, you can see I have the original transient generator out along with our high voltage probe. So the scope right now is set for 2000 volts per division. And you can see it's 5 microseconds per division right now. And you can see we are about 3.5 divisions up, or roughly 6500 volts. This is the last transient that I had applied. You can see we're still at 2000 volts per division. And this is 20 microseconds per division. And you can see we're 4 divisions up. So this is the wave roughly that we're going to be applying. Of course, I have a load attached to this right now. This will be a 8000 volt peak with a 2 ohm source impedance. Again, we'll be applying 5 transients with each mode of the meter, and then I'll perform a functional test on it. We'll check it for any damage. Again, the meter right now is running off an external battery pack. Again, I want to make sure that we don't have any kind of a current loop. Alright, let's go ahead. Again, this is what the transient looks like. This is the transient as it's being applied to the clamp circuitry. Alright, that's it. Let's just remove the leads. Let's place it in resistance mode. Looks fine. Let's try it. So in temperature it reads an open. Let's try capacitance. My guess is it's going to be fine. Let me go ahead and functional test it. Okay, so our Fluke 189 survived that test. So I've gone ahead and changed our generator. You can see we're still at 2000 volts per division, but I now have roughly a 4000 volts offset. And you can see we're 20 microseconds per division. So we are currently 5 divisions up, or 10,000 volts. And 2.5 divisions up would be here. And it's roughly 2.5 divisions out, or 50 microseconds. Alright, again, I'll be applying 5 transients. Looks pretty good. Well, looks pretty good. I'll just let you watch one come in live. Right there. Let's just check resistance real quick. You can see it's still an open. Let's try capacitance. Go back to temperature. Again, all I've done is reverse the polarity. So this is with an open. Let's just put a 1K on there real quick. That looks good. Let's try capacitance. So again, I won't compensate these, but this is a 0.1 mic. This typically reads 102. That looks fine. Let's try it in temperature. Again, this should be roughly 500 degrees Celsius. And again, we can adjust that. This will be roughly room temp. And the meter reads just over 1000 degrees. This should be roughly 20. It looks good. Wasn't paying attention, but the battery light had been on. So I'm now running off of our bench power supply. So let's run a few other modes. So this will be roughly 70 volts. And this should be about 118. Let's try it in millivolts. So again, about 118. And this should be 2.5. And this should be 2.5. This should be 5 volts. Should be roughly 2.5. and that should be roughly 2.5. So I'll go through and run the rest of the meter, but it looks like it's fine. Alright, so it looks like the Fluke 189 has survived all these tests. So again, if we look at the 10,000 volt column, so this is the test we just performed, you can see that I did not test the Fluke 107 at this level. I had gone all the way up to the 13,000 volt, 100 microsecond volt with half height. This was the level that I tested the Fluke 101 at, and then I took it up higher until it failed. This meter here that failed at 10 kV is that Fluke 17B plus. But again, going down through here, you can see there's not very many meters that have survived to this level. So again, this meter being roughly 18 years old, that's pretty impressive. So I think that's going to be it for the transient testing for this meter. And I think this will be the end of the video as well. So I hope you enjoyed seeing this old vintage Fluke come back to life. Maybe you'll see it in some future videos. Again, the case that was supplied with this meter is in pretty rough condition. This would actually make a pretty good parts meter. Maybe if I find another one that has extensive electrical damage, you know, but a good case, I can steal the case and put these innards inside of it. Again, the only thing that's really wrong with this is just that one switch contact. Well, that's going to be it for now. Till the next video. Later.